Today we are very excited to be able to have a Nobel Prize winning physicist come talk to you. I think you'll find it to be an extremely exciting and informative presentation. Before we do that, I want to welcome a few people. I'd like to welcome Phelps School, I'd like to welcome Langley Education Campus, and I'd like to welcome Ballou. Thank you. Thank you very much. Thank you very much for joining us as we all seek in the district to make ourselves more knowledgeable. I'm glad that you can join us. There are a few people that need to be thanked. First off, I'd like to thank the MIT Club with Ken Gordon and George Moy and their tireless work in helping to make this a reality. Also, I'd like to thank NIST, the National Institute of Standards and Technology, for their help in making sure that this event runs smoothly and we all get to appreciate it. I want to take a moment to introduce Dr. Phillips. Dr. Bill Phillips won the Nobel Prize in Physics in 1997, which he shared with two others, for pioneering work in development of methods to cool and trap atoms with laser light. He did this prize-winning work at the National Institute of Standards and Technology in Gaithersburg, Maryland. However, you need to know a little bit about Dr. Phillips's upbringing. His parents moved to Camp Hill near Harrisburg, Pennsylvania in 1959, where he attended high school and graduated valedictorian of his class. He graduated from Juniata College in 1970, summa cum laude. After that, he received his physics doctorate from the Massachusetts Institute of Technology, MIT, which you may know is in Boston, Massachusetts. And of course, Ken Leslie, our engineering teacher, is a graduate of that fine institution. Dr. Phillips's doctoral thesis concerned magnetic moment of the proton in H2O. This led to connections that would be important later in his research. In 1997, he won the Nobel Prize in Physics for his contributions to laser cooling, and especially for his invention of the Zeeman slower, a technique to slow the movement of gaseous atoms in order to better study them at NIST. He was one of 35 Nobel laureates who signed a letter urging President Obama to provide a stable $15 billion budget per year to support clean energy research, technology, and demonstration. Dr. Phillips is married to Jane Van Wynen shortly before he went to MIT, and they have two daughters. What isn't talked about often is that Dr. Phillips wasn't some privileged kid who went to the finest schools. He's the son of social workers from Pennsylvania coal country and got where he is through hard work and, of course, very considerable talent. He spends a great deal of time talking to young people and lay audiences in the United States and around the world about the joys and importance of careers in science, and is, correctly, regarded as one of the nation's leaders in communicating science to the general public. Ladies and gentlemen, I introduce Dr. Bill Phillips.
Thanks very much. Thank you. Thank you very much. It's a great pleasure for me to be here at McKinley today. As you heard, I'm Bill Phillips. I come from the Joint Quantum Institute, which is a joint operation of NIST, the National Institute of Standards and Technology, and the University of Maryland. And at NIST, I'm a member of the Laser Cooling and Trapping Group, and it's a tremendous privilege for me to work with Gretchen Campbell, Paul Lett, Trey Porto, and Ian Spielman, and a host of young men and women who have joined us from all over the world and all over the country. The genesis of this talk came from the MIT Club, and it's brought to you by NIST and by the Physics Frontier Center at the JQI, supported by the National Science Foundation. And the Office of Naval Research of the U.S. Navy has supported this work from the very beginning and continues to support it. And the National Science Foundation supports the latest developments in this field. So, let's get to it. Time, Einstein, and the coolest stuff in the universe. We're going to talk about some really cool stuff, and we're going to have some fun today. And just to give you an idea, before we get started, of the kind of fun we're going to have, yeah. People, this is the coolest stuff you've ever seen. And I'm going to explain to you exactly what that's all about in just a little bit. But right now, time and Einstein. So what does time have to do with Einstein? Well, Time put Einstein on the cover of a magazine as the person of the century. And with very good reason, because Einstein discovered all sorts of things that have changed our thinking about the nature of the universe and are continuing to influence science and technology in the 21st century. He did so many things, but probably the thing that Einstein is most famous for is his theory of relativity. The famous equation, E equals mc squared, comes from this theory. And the theory of relativity was so revolutionary that it changed the way we think about the very nature of space and time itself. Before Einstein, people thought that space and time was like this stage, and the events of the universe play out on this unchanging stage. But what Einstein was able to figure out was that that stage is not unchanging, that that stage depends upon the circumstances and it depends upon who's looking at it. And the way in which he came to understand these revolutionary ideas about time was by asking himself a question that I suppose people have asked themselves since the beginning of time. What is time? What is this thing that goes from being the future to the present to the past, but is always in the present? What is this strange thing that we call time? And the answer that Einstein came up with may seem to you a bit superficial, because he said that time is what a clock measures. But by taking seriously the idea that time is what a clock measures, Einstein changed our very ideas about what time is. But if time is what a clock measures, what is a clock? Well, for me, a clock is something that ticks, something that gives you a set of periodic events that allows you to tick off days or hours or minutes. The oldest clock is the rotating Earth. As the Earth rotates, we see the sun rise and set, and we tick off days. As people became more sophisticated, they made sundials, and they ticked off hours. Many, many centuries later, the famous scientist Galileo was, according to legend, sitting in church in the cathedral in Pisa, and apparently he wasn't paying too much attention to the service. Instead, he was watching the chandelier, and he watched the chandelier swing back and forth. And he noticed that it didn't matter how far the chandelier would swing. If it would swing a little bit, the time that it would take to make a full swing would be the same as if it swung a lot. And this was the beginning of the use of the pendulum as a ticker for a clock. And so people made these beautiful and very accurate clocks using a pendulum as a ticker. Some of you may be wearing a wristwatch, and probably in that wristwatch is a quartz crystal like this one. And the vibration of that quartz crystal is the ticker for that quartz watch. Now, ever since the beginning of the 20th century, the National Institute of Standards and Technology, NIST, where I work, has been charged with making better and better clocks. And we've never been out of a job, because all of these clocks, whether it be the Earth or the pendulum or the quartz watch, all of these clocks are imperfect. For example, If the length of a pendulum changes, then its ticking rate changes. A short pendulum ticks faster than a long pendulum. And with heat and humidity, the length of the pendulum might change, and that will change the ticking rate. Every quartz crystal in every watch is a little bit different and keeps time a little bit differently. Even the rotation of the Earth is affected by things like the tides and changing ocean currents, storms. The fact that the rotation of the Earth is not a constant was made clear to me in a rather dramatic way one day when I visited the U.S. Naval Observatory. I was visiting a colleague there who was going to show me the latest in clocks that they were making at the U.S. Naval Observatory. And as we were walking down the corridor, we passed by a door, and on the door it said, Director of Earth Rotation. Pretty responsible job, I would think. But the point is that the rotation of the Earth is not constant. It changes, and somebody has to keep track of how much it changes in order to keep sun time the same as the more accurate time. And what is that more accurate time? That more accurate time is given to us by the thing that ticks the most regularly, and that is the ticking of atoms. Atoms are the best tickers. Every quartz crystal is a little bit different from every other one and vibrates at a different rate. But every atom of the same kind ticks at exactly the same rate as every other atom of that kind. By international agreement, we have set the length of time that we call a second equal to a certain number of vibrations of the cesium atom. And every cesium atom of this isotope, every cesium-133 atom, throughout the entire universe, as far as we know, is absolutely identical to every other atom of that kind and ticks at exactly the same rate. And that means that if somebody makes a clock in Boulder, Colorado, and somebody makes a clock in Paris using cesium as the tickers, those two clocks are going to keep the same time. And that's why atoms make the best tickers. They're also very little affected by things like temperature and humidity, so they make the best tickers. These are the best clocks. Well, how good are these clocks? Well, for less than $100, you can certainly buy a watch like mine that is accurate to a part in a million. In other words, about 30 seconds in a year. If you're willing to spend $100,000, then you can get an atomic clock that is good to a part in a million. That means 30 seconds in a million years. Now, you may wonder, $100,000 for a clock, that's an awful lot of money. But think about this. You spend 1,000 times more money, and you get 1,000,000 times better performance. I think that's a bargain. But you still may wonder, who really needs a clock that's that good? Because after all, most of us, for the kinds of things that we do during our daily lives, don't need to know what time it is to that kind of accuracy, or so you may think. What I would like to convince you about is that you are very happy that at least somebody knows what time it is to that kind of accuracy. I found this advertisement once in a magazine for a high-end car. It says, if you get into trouble, relax, because help is only 10,000 miles away. And the 10,000 miles referred to is the orbiting altitude of the satellites of the Global Positioning System. The Global Positioning System is a set of satellites, at least 24 satellites, orbiting the Earth at an altitude of about 10,000 miles. And every one of those satellites has on board atomic clocks. And a receiver that you might have in your car, that a delivery truck might have on its dashboard, that commercial airplanes use to guide them from airport to airport, those receivers get the information from the atomic clocks on board those satellites, and from that information they can figure out where they are. People use this for all sorts of things. When they go hiking in the wilderness, people take a GPS along so they won't get lost. Even golfers use it. I'm pretty sure that if you talk to Tiger Woods' caddy, he's probably telling the star golfer, how far away he is from the hole using a GPS. Well, how does this work? Well, the idea is that you've got these satellites. So here's a satellite, and on board that satellite is an atomic clock. And here's another satellite, and on board it is an atomic clock. Now let's just imagine for the moment that your GPS receiver also has an atomic clock. That's not the case, but let's just imagine for the moment that your GPS receiver has an atomic clock in it. And all these atomic clocks are synchronized, so they're all keeping the same time. Right now, the time is 1 in these units. And those clocks are broadcasting information about what time it is, and they're broadcasting information about where all the satellites are. So here's what happens when the satellites are broadcasting the information. You see, it takes a certain amount of time for the signal about what time it is to reach the GPS receiver. So when the time is 4 and all the clocks are reading 4, the signal from this clock reads 1 because it was a little time before that the signal left the clock when the time was 1. If we keep running forward in time, whoops, let's go back. So it takes a certain amount of time for the signal to get to the receiver, and by looking at the delay, you can figure out how far away the satellites are. So by the time you get to here, you know how far away you are from this satellite because you can see what its signal reads. You know how far away you are from this satellite because you can see what time its signal reads. And if you know how far away you are from two things, and you know where those two things are, then you know you're somewhere on the intersection of these two circles, so you're either here or here. Well, that's what happens in 2 dimensions, but we live in a 3-dimensional world, so you need 3 satellites, and you don't have a clock on your GPS receiver, so you need a 4th satellite. That's your clock. So anytime you can see 4 satellites, you can figure out, your GPS receiver can figure out where you are anywhere on the face of the Earth to within a few meters. It's only because we have such atomic clocks that the GPS system works. And we're always trying to make clocks better so we can improve GPS. Other things, we improve high-speed synchronous communication. Scientific research and national security applications, we're always trying to improve these atomic clocks. Now, if you were to go to our clock laboratories in Boulder, Colorado, you might see an instrument like this. I'm not sure they've got this sign on the wall, but the point is that this is what our atomic clocks look like. And atomic clocks like this are incredibly accurate. The clock like the one in this cartoon is accurate to better than a part in 100 million. The problem is that we'd like it to be even more accurate, and we can't get it to be more accurate because the atoms inside the clock are moving so fast. Now, why is that a problem? One of the reasons why it's a problem is because of something called the Doppler shift. If you've got a source of waves that's broadcasting something like the ticks of a clock, and you move toward that source of waves, you're going to see the ticking frequency increase. Imagine this. Imagine that you were on the seashore and you're watching waves come in. They come in at a certain rate, and you could think of that as being a ticking frequency. But if you were to get into a boat and head into the waves, you would find that the waves would hit your boat faster than they would hit the shore. That is, you'd get a higher frequency of waves hitting the front of your boat than you would hitting the shore. That's the Doppler shift for ocean waves, and it works for sound waves, and it works for radio waves, and it works for light waves. This, people, is how the cops tell how fast your car is going. They send out a microwave signal. It bounces off of your car, and if your car is moving, then the frequency of the microwaves coming back is higher, and all they have to do is measure the shift in the frequency, and that tells how fast your car is going. But that produces disastrous effects for atomic clocks. How big is this effect? Well, it doesn't seem very big to you and me. The fractional change in the ticking frequency is the ratio of the atom's velocity to the speed of light. Now, how fast are the atoms going? Well, take the molecules of nitrogen in the air in this room. They're moving at about 300 meters per second, about the speed of sound. The speed of light, on the other hand, is about 300 million meters per second. That means that the shift is a part in a million. That sounds like a really tiny shift, but we're trying to make clocks that are better than a part in 100 million. That means this shift is 100 million times bigger than the kind of accuracy we want in our clocks. So this is a disaster. But over the years, people at NIST and elsewhere have come up with all sorts of tricks to reduce this effect. But what's left over is the thing that makes it difficult to make the clock any better. So because of Doppler shifts, and also because of the fact that the atoms are moving so fast, you just don't have very long to look at them, these clocks, like the one that was in that cartoon, these clocks just can't be made any better unless we make the atoms go more slowly. And that means cooling the atoms. Why does making them go more slowly mean that we have to cool them? Because the difference between hot and cold is the difference between fast and slow. If I have a gas of atoms, and the gas of atoms is really hot, it means that they're moving around really fast. The molecules in the air in this room, for example, moving at about 300 meters per second. If you could cool down the air in this room, and it's kind of hot in here, and I think maybe it would be a good idea if we could cool down the air in this room. If we could cool down the air in this room, what that would mean is that we would be making the atoms and molecules move more slowly. So now, to give you an idea of just what I mean and how cold we would like to get, I brought along this really, really cool stuff. What I have inside here, what's inside this container is liquid nitrogen. Nitrogen is the main constituent of the air. That means that what's inside here is essentially liquid air. This is so cold that compared to it, the floor on which I'm standing is red hot. The boiling point of liquid nitrogen is so low that the temperature of the floor is so much higher than its boiling point that when I pour it out on the floor, it boils immediately. That's what's going on. Because the liquid nitrogen is so cold, it boils immediately when I pour it on the floor. Now, if you've got something that is that cold, then it seems like it would be a good idea to use it to refrigerate a gas to make the atoms and molecules move more slowly. So here I have a traditional container for hot gas, and I'm going to fill it up with some hot air, and I'm going to put it into this bucket. I'm going to put it into this bucket of liquid nitrogen so that we can cool it down to make the atoms and molecules move more slowly. Now, let's see if I can do something to show you just how cold this stuff is. Here is a container that we call a Dewar flask. It's really just a thermos bottle. It has been sitting out on this table all day. It is at room temperature. That means that compared to liquid nitrogen, this thing is burning hot. Imagine what would happen if you took a metal bucket and heated it up until it was red hot, and then poured cold water into it. It would boil. And that's what's happening here. It's boiling away, cooling down the inside of that container. So while that's happening, while it's cooling down the inside of the container, let's cool down some more hot gas. Got to be careful not to make it too big so that it won't fit. Okay, good. Now, coming over here, I look inside and I see that a lot of the nitrogen has boiled away. So I'm just going to top it up. And now, I'm going to take this nice fresh flour, okay? Nice flour. The flour is at room temperature. That means that compared to the liquid nitrogen, this flour is red hot. In fact, it's actually red. Imagine what would happen. Imagine what would happen if you took something like a fireplace poker, a metal rod, and heated it up in the fire until it was red hot, and then took that and plunged it into a bucket of cold water. What would happen? It would make the water boil. And that's exactly what's happening here. So it's boiling away, and that means that the flour is cooling down. So while the flour is cooling down, let's cool down some more gas. Because, you know, if we want to have some cold gas so the atoms and molecules are moving more slowly, we might as well have a good bit. Okay. Because we want to cool down the atoms and molecules in the air, because if they're moving more slowly, then we'll be able to measure them better. So now coming back to the liquid nitrogen and the flour, I see that the boiling has subsided. That means that the flour is now down to the temperature of the liquid nitrogen. This thing is frozen so hard that when I take it out, I can crush it. People, this stuff is really, really cold. And if you've got something that cold, well, why not use it? Why not use it if you want to cool down a gas to make the atoms move more slowly so that you can measure them better? Okay, great. Now, let's see, what else can we do? Here is a racquetball, okay? Nice bouncy racquetball, right? Let's put the racquetball into the liquid nitrogen to see what happens. And while that's cooling down, here's a rubber band. Nice stretchy rubber band, right? I'm going to take this pair of tongs, dunk the rubber band into the liquid nitrogen. Now, it's making the nitrogen boil because it's at room temperature. It's really, really hot compared to the liquid nitrogen. But the boiling subsides after just a little while. That means the rubber band is cooled down to the temperature of the liquid nitrogen. It is frozen so hard I broke that rubber band like it was a dry twig. But now that I've warmed it up in my hands, it's nice and stretchy again. Now, I'm sure that your mother or your grandmother has told you that when you're cooking something in the kitchen, you should never, ever take a closed container of liquid and put it into the oven. Now what I've got here is a container, soda bottle, and I'm putting some liquid nitrogen into it. Now the point is that compared to the liquid nitrogen, this room is an oven. So let's just see what happens. Now let's get the, so remember how nice and bouncy the rubber ball was? Let's see how it bounces now. Kids naturally, like you, are curious about the way things work. And somehow, as people grow up, most of the people lose that curiosity. But you know what? There is a certain class of people who don't lose that curiosity, and those people are called scientists. My friends, scientists are just kids who never grew up. And so I hope that you will never grow up in the sense that you will never lose. And that, my friends, is why, you must never put a closed container of liquid into an oven. Okay? Your mother was right. Never, ever put a closed container of liquid into the oven, because that's what will happen. You know, this thing is falling off. Okay, I think we're back. Okay, are the sound engineers happy with the way this thing is now? Because it was falling off. Okay, so how cold is this? Well, scientists like to measure temperatures in a different way from the way most people measure temperatures. Most people measure temperatures in degrees Fahrenheit or degrees Celsius. But scientists use a different scale. And the scale we use is called the absolute or Kelvin temperature scale. Now, on the absolute temperature scale, the lowest temperature that you can possibly have is what we call 0. Now, why is there a lowest temperature? Let's think about that for a minute. Why is there a lowest temperature that something can be? Look at this. Remember, the difference between hot and cold is that a hot gas has its atoms and molecules moving around really fast, and a cold gas has them moving really slowly. What is the slowest that you can go? The slowest you can go is stopped, and that's why there is a lowest possible temperature. So that lowest possible temperature is what we call absolute 0, the temperature at which the motion of things stop. Now, it turns out that even at absolute 0, the motion doesn't exactly stop. There's a little problem with quantum mechanics and Heisenberg's uncertainty principle, but let's forget about that and just say that between us friends, that absolute 0 is the temperature at which the motion stops. On that scale, where 0 is the temperature at which motion stops. Room temperature is about 300 degrees, 300 degrees Kelvin above absolute 0, where the degrees are the same as Celsius degrees. Now, to just give you an idea, ice melts at 273. Remember Snowmageddon? Cold, snowy day, 260 degrees above absolute 0. Take an ice cream bar out of the freezer, probably about 255 above absolute 0. Dry ice, really cold stuff, 195 degrees above absolute 0. The coldest temperature that anybody ever measured anywhere on the surface of the Earth, someplace in Antarctica during the winter, 185 degrees above absolute 0, the coldest air temperature ever measured anywhere. My friends, this stuff that is so cold that so cold that when I pour it out on the ground, it boils. This stuff is 77 degrees above absolute 0. This stuff is really, really cold. 77 degrees above absolute 0. Just look how much colder than all these other incredibly cold things we have is. And so it seems perfectly reasonable that if you've got something that's that cold, then it might be a good idea to use it to cool down your gas, which is what we did by putting these balloons in. Now, one of them popped out, but the point is that a lot of you realized that I put more balloons in here than there was room for. And the reason is these balloons are as flat as pancakes. They're like Frisbees. Does anyone remember how many balloons I put in there? What I put in blue balloons, and I put in a green balloon. How many yellow balloons did I put in? How many orange balloons did I put in? There's another orange one. People, I could have kept putting balloons in there until the cows came home, because those balloons went flat as pancakes. Now, why did that happen? Watch the movie. Watch the movie. What was going on was that when the balloon is out at room temperature, the atoms are moving around, they're free, but they're moving fast. Now, they went into the liquid nitrogen, and they started to slow down, but what finally happened was they condensed. They turned into a liquid or a solid, and that's why the balloons went flat. They're frozen. They're stuck. Now, the problem is that if you're trying to make a clock out of atoms as tickers, in order to get that perfect ticking frequency, the atoms have to be floating freely in space, like the atoms in this balloon, but they're moving too fast. The trouble is, when we tried to cool them down with the coldest stuff you've ever seen, liquid nitrogen at 77 Kelvin, 77 degrees above absolute 0, they condensed. You didn't have a gas anymore. And you can't make a clock with atoms that are stuck to each other. They're just not right. So the question is, how are we going to get a gas of atoms really, really cold and not have them condense? So that's one problem. How are we going to get a gas of atoms really, really cold and not have them condense? But there's more. Because the temperature of 77 degrees, even though it's the coldest thing that you've seen, I mean, unless you have been in a low temperature physics laboratory, liquid nitrogen is the coldest stuff you have ever seen. At 77 degrees, it's approximately 4 times closer to absolute zero than room temperature is. Temperature is a measure of energy. Energy goes like the square of the velocity. That means that the velocity of the liquid nitrogen that you would pour out onto the ground, when it evaporates from the ground, the nitrogen that is coming off at a velocity of half as fast as the molecules of nitrogen that are in the air in this room. Half as fast. 150 meters per second. That's a big reduction, a factor of 2. Half as fast. But you know what? I have been working on this for more than 30 years. And I have not devoted 30 years of my life to make half-fast atoms. What I wanted to do was to make things that were really, really slow. So how are we going to do that? Well, in a certain sense, the answer to that question has been staring at us from the heavens for centuries. This is a picture of a comet. And since the time of Kepler, centuries ago, people have known that the tails of comets point away from the sun. When a comet comes in from the outer reaches of the solar system, the sunlight warms it up, and it evolves dust and gas. But more than that, the sunlight pushes on the dust and gas and makes the tail stream out. So as the comet comes in, the tail streams behind the comet, and as it goes around and comes back out, the tail streams in front of the comet. And that's because the light from the sun pushes on the dust and gas and makes the tail stream always away from the sun. What we're going to do is to use that pressure of light to push on the atoms in such a way as to make them slow down. Now, how is that going to be possible? How can we shine light on something and make it get cold? Normally, if you shine light on something, it gets hot. The lights in this auditorium are certainly making me hot. Why is it that we can shine light on a gas and make it cold? So now you really got to pay attention, because here comes the real physics part. There's 2 things that you got to understand. One of them is the concept of resonance. If I've got an atom and I shine light on the atom will not absorb the light unless the light has just the right color. Now, the color of light is determined by the frequency of the light. Light is an electromagnetic wave, just like radio waves, just like microwaves. Light is an electromagnetic wave. Your radio, if you listen to AM, you're listening to something that's about 1 megahertz, 1 million cycles per second. If you listen to FM, then you're listening to something that's at 100 million cycles per second. Light is at about 1,000 million cycles per second. And what the exact frequency is determines what the color of the light is. And if the color isn't just right, the atoms won't absorb the light. And if they don't absorb the light, they won't feel any push. Now, the color has to be just right. If you make the color different by a part in 100 million, then the atoms will not absorb the light. You would never be able to tell the difference between 2 colors that are different by a part in 100 million, but the atoms can easily tell the difference because the atoms are so sensitive to the color of the light. They're exquisitely sensitive to the color of the light. That's the first thing you need to know. The second thing we've already talked about, the Doppler shift. If I've got light moving toward this person, and the person is moving toward the source of the light will appear to have a higher frequency. Just like when you get in a boat and go into the waves, it looks like the waves are hitting you at a higher frequency. So when you move toward the source of light, it looks like it's a higher frequency. That means the light will be shifted from the red toward the green toward the blue. The effect is really, really tiny. It would be a really bad idea if you were stopped for going through a red light and you explained to the police officer that you were moving toward the red light, and because of the Doppler shift, it looked green. Because you would have to be going so fast that it would be close to the velocity of light, and I think the speeding ticket would be a lot worse than the red light violation. But atoms are so exquisitely sensitive to the color that they can see the difference. So now you know what you need to know to understand why it's possible to cool down a gas by shining light on it. So here's a cartoon of a gas. Some of the atoms are moving to the right, some of the atoms are moving to the left. Here is a laser beam coming in from the left, tuned a little bit below the resonant frequency of the atoms. Now imagine that I'm this atom going this way. I'm looking at this light, and it's too red if I were stopped, but I'm moving. And because I'm moving, the frequency of this light appears to be higher, and so it's the right frequency for me to absorb. I absorb the light, and I slow down. This atom, going this way, looks back, and it sees the frequency even lower than it would be if it was at rest. So it doesn't see that light at all, or hardly at all. If it did, you see, it would be speeded up because it would be pushed in the direction that it's going. But because the light appears to be the wrong color, these atoms don't get accelerated. Now, you just bring in light from the other direction. This atom sees this laser beam as having the right color, and it slows down. This atom sees this laser beam as having the right color, and it slows down. And so no matter which way the atom goes, it will slow down. Now you can take this one-dimensional model and make it in 3 dimensions. So you have laser beams coming from top and bottom and backwards and forwards. And now no matter which way the atom goes, it sees that those laser beams that oppose its motion are the ones that have the right color to be absorbed. It absorbs them, and the atoms slow down. It is as if the atoms were in a swimming pool of molasses. Imagine you were in a swimming pool full of molasses. If you tried to move, you would immediately feel that there was a force that was opposing your motion. And so when my friend and colleague Steve Chu first did this at Bell Labs in 1985, he was one of the ones who shared the 1997 Nobel Prize, and he's now the Secretary of Energy. When he did this in 1985, he called it optical molasses. So that's not the end of the story. If that was the end of the story, then the atoms would just come to rest. They don't. The reason the atoms don't come to rest is because of what Einstein taught us at the early part of the 20th century, that light should be thought of as particles. And because light is a particle, that means that when an atom absorbs light, it does it one particle at a time. We call those particles photons. Let's imagine that I'm an atom, and there's laser beams coming from the left and from the right, and they both have the same color and the same intensity. It's completely random whether I will absorb light from that side or from that side, but it'll be from one of the sides, and then I'll get a kick, and then I'll start moving at about 3 centimeters per second if I'm a sodium atom. And then I want to get rid of that extra energy, and I do it by radiating a photon. It's like shooting off a gun, and there's a recoil, and the atom jumps back and changes its velocity again, ready to absorb another photon, maybe from this side, and then it gets a kick in this direction. Every time the atom absorbs and emits a photon, it gets a kick, and it does a kind of a random dance, and that heats it up. And so there's a balance between the heating and the cooling, and the atom finally comes to some final temperature, and you can calculate what that temperature is, and according to the calculation, that temperature could be as low as 240 millionths of a degree above absolute zero. 240 millionths of a degree above absolute zero. Think how cold that is. This stuff is the coldest stuff you've ever seen. It boils when you pour it out on the ground. It's 77 degrees above absolute zero. This theory said that you could get a gas of atoms 300,000 times colder than that. That was pretty spectacular, and so people got to work. We got to work, Steve Chu got to work, and here is a picture from our laboratory of a cloud of sodium atoms about 1 centimeter across. There's laser beams coming in from all directions. And these laser beams are cooling those sodium atoms. How cold have we been able to get things? Well, let me remind you of the absolute temperature scale, where room temperature is up here and absolute zero is down here. Let me put one more mark on that thermometer. Outer space. If you go to the outer regions of space, far away from any stars or planets, space is filled with radiation left over from the Big Bang 14 billion years ago. And the temperature of that radiation is about 3 degrees. That's the coldest natural temperature in the universe, 3 degrees above absolute zero. The theory said we could get down to a quarter of a thousandth of a degree above absolute zero. But when we really got into it, we found, in fact, that we could get even colder. Eventually, with cesium atoms, we got down to a temperature of 700 nanokelvin. That's 700 billionths of a degree above absolute zero. 7/10 of 1 millionth of a degree above absolute zero. That temperature is 100 million times colder than liquid nitrogen. And liquid nitrogen is the coldest stuff you've ever seen. It boils when you pour it out on the ground. That temperature is 4 million times colder than outer space. So when I say the coolest stuff in the universe, I'm not kidding. This stuff is incredibly cold, and one of the most exciting things was that this temperature was 200 times colder than everyone thought was possible. Now, unfortunately, I don't have enough time to explain how that came about, but finding out something that nobody imagined is one of the most exciting things that can happen to a scientist. You're lucky if something like that happens to you once or twice in your life, and this was an incredibly exciting thing to have happen, to find out that what everyone thought was in fact wrong and that we could get atoms a whole lot colder. Well, the whole idea was to make these atoms cold so that we could make better clocks. So what kind of clocks have we been able to make? Here is a picture of one of those clocks in our clock laboratories of NIST out in Boulder, Colorado. That is Don Meekoff and Steve Jeffords, and they cool atoms down here. They shoot them up, they come back down after about a second. You see, it's a wonderful thing. If you toss something up vertically at about a meter per second, a couple of meters per second, it comes back down after a second. And that means you get a whole second look at these things. These things are moving much, much slower than ordinary thermal atoms. And these clocks are now accurate to a second in 100 million years. And in other experiments out in Boulder, we have clocks that are made with electrically charged atoms, ions, and they're good to 1 second in a billion years. 1 second in a billion years. This is what NIST, the agency of the US government whose business is measuring stuff, this is what we're doing for you. And a second in a billion years is what we call close enough for government work. But you might ask yourself, if you have a gas this cold, where do you keep it? I mean, after all, no ordinary container is going to be able to hold a gas at a temperature of 1 millionth of a degree above absolute zero. Imagine that this bowl is the container that I would like to hold my cold gas in. I don't know how I could make a container like this as cold as the gas, but if it was as cold as the gas, then what would happen would be the gas atoms would just stick to the inside and I wouldn't have a gas at all. Now, if the container is hot, then that means that all the atoms and molecules that make up the container are moving around really fast, and so it's going to heat up the gas, and it'll just heat the gas up so hot that it'll leave the container and I won't have any gas at all. So I can't use a container like this. What I've got to do is use a magnetic bottle. Now, what is a magnetic bottle? Have you ever played with magnets? Do you remember the first time that you held two magnets in your hand and turned them just the right way and felt that they were pushing each other apart? Wasn't that amazing? I'm still amazed by that. Well, that's the idea of a magnetic bottle. So let's go over here and look at these magnets that I've got here on this table. Okay, so what I've got is little magnets, and you'll notice that I can push on the one magnet with the other magnet without touching it. And that idea of pushing on something without touching it is what we're going to use to make our magnetic bottle. So here, we have this up now? So here I've got a big magnet, okay? This part right here. Okay, this is a big magnet, and it has been arranged in such a way that it is pushing up on this little magnet. This little magnet represents our atom, and the big magnet represents what we call our magnetic trap. Now, the big magnet is pushing up on the little magnet so that right here it's pushing up just enough that it should keep this little magnet levitated above the big magnet. And so if I let go of it, it should just float. But when I do let go of it, what happens instead is that it flips over and it gets attracted to the big magnet. So this never works. If you want to try to levitate one magnet with another magnet, that will never work unless you do something a little more clever that you learned about when you were children. Because you probably played with a top. A spinning top will stand up instead of falling down. And it turns out that our atoms are like little spinning tops that are also magnets. So what I'm going to do now is to spin the magnet and then raise it to the point where it's just pushed up by the big magnet. But wait a minute. As you probably know, I'm sure you've seen a magician who can levitate a woman, and then after the magician has levitated the woman, he'll pass a ring around her, carefully avoiding all the wires that are holding her up. You've never seen a magician do this. There's nothing holding that up. This is the real thing. Now let's go back to the computer. Thank you. So that was the toy version. That was the toy version of our magnetic bottle for atoms. Now I want to show you the real thing. This is a movie of a sample of atoms cooled down to about a microdegree and then released into a magnetic trap. So here goes. So this is a cloud of atoms that has been released into a trap, and now it's bouncing around a little bit like our toy top was bouncing around. And as time goes on, the atom cloud dissipates, and the reason is that the vacuum is not perfect. So that's how we hold our atoms. Now, since that movie was made, we've learned how to make a much better vacuum. And using a magnetic bottle as a container for ultra-cold atoms, we can use another trick for getting the atoms even colder. And the trick is called evaporative cooling. Now, you all know what evaporative cooling is. If you've got a cup of tea or a cup of coffee and it's too hot to drink, the way you cool it down is you blow on it. And what's happening is that the most energetic of the water molecules escape from the surface of your tea or your coffee, and what is left behind has a lower energy and therefore has a lower temperature. That's how you cool your coffee off. We do exactly the same thing with our atoms. We hold them in a cup, but that cup is a magnetic trap. We allow the most energetic ones to escape, and as a result, the ones that are left get down to temperatures of less than 1/billionth of a degree. And when the gas gets that cold, one of Einstein's strangest predictions comes to pass. In this gas, a large fraction of the atoms essentially stop moving. This is the best you could hope for in making a sample of atoms that you can study as well as possible. And this phenomenon is called Bose-Einstein condensation. It was first achieved in 1995 in the laboratories of NIST out in Boulder, Colorado, and the people who did it got the Nobel Prize in 2001 for that accomplishment. So now we've come to the end of a sort of an odyssey of looking for colder and colder temperatures. And to illustrate that to you, I've got this cartoon of a thermometer. This is called a logarithmic thermometer, and what that means is that every tick mark on the thermometer represents a change of a factor of 10 in the temperature. Now on this thermometer, the surface of the sun is at the top. This is not the hottest temperature that there is, but it's pretty hot, surface of the sun, 5,000 degrees Kelvin. Room temperature, 300 Kelvin, is just a little colder than the temperature of the surface of the sun in this cartoon. Liquid nitrogen. Remember, liquid nitrogen, so cold that it boils when you pour it out on the ground. That was disappointing. Let's have some more. 77 degrees above absolute zero, the coldest stuff you've ever seen, just a little bit colder than the surface of the sun. Even the temperature of outer space on this scale is only a little bit colder than the surface of the sun. Look how much colder laser cooling got than the temperature of outer space. Laser cooling got us to temperatures colder compared to outer space than outer space is compared to the surface of the sun. And outer space is the coldest natural temperature in the universe. But that was just the beginning, because evaporative cooling and Bose-Einstein condensation has now reached temperatures lower than 1/1000th of a degree. The difference between the first, well, not even the first laser cooling, but the lowest temperatures we got with laser cooling, the lowest temperatures we got with evaporative cooling, is colder compared to laser cooling than outer space is compared to the surface of the sun. And that's just the beginning, because we're imagining, we're dreaming about experiments that we might take into the space station and get another factor of 1,000 colder. If this thermometer were an ordinary thermometer with a linear scale, where each tick mark represents the same amount of temperature, and if the top of this thermometer were on the moon, the lowest temperature that we now have would only be as high as the thickness of a human hair. That's how cold we have things. If instead this was a linear scale and the top of the thermometer were as high as the projection screen, the lowest temperature would be 1/1000th the size of a single atom. This stuff is incredibly cold. And with stuff this cold, we've made better clocks. Today, the kind of clocks that I showed you, the pictures of from Boulder, are guiding the GPS system and making the global positioning system better all the time. These clocks are being used for better tests of Einstein's theories of time and gravity. They're being used, that is, cold atoms are being used to give us new understandings of materials and to build computers that, if they can be built, will be more powerful compared to present-day computers than present-day computers are to the ancient abacus. And maybe the most exciting things will be the things that some students from McKinley Technology High School will think of. Because if some of you, as I hope you will, don't lose your childlike curiosity and decide to pursue a career in science, you may be privileged, as I have been, to work with a group of young people from all over the country and from all over the world, working together and sharing ideas and learning from each other how to do more and more exciting things and how to learn more and more about this wonderful universe that we live in. Well, I hope that this afternoon I've been able to share with you a little bit of the adventure that those of us who do this kind of work have experienced. And not just adventure, but I hope that I've been able to share with you how much fun it is to do this sort of work. And so we come to the end, but not the end, because there's always something new to learn when you're studying science and the way our world works. Thank you very much. Thank you.